Hello there, welcome to chapter 7.3, and in this video we're going to be looking at elimination and addition reactions. I'll explain the breakdown of each video on the next slide. In the first half of this lecture, that's videos 1 and 2, we will revisit aspects of substitution and elimination reactions. More specifically, in video 1, I'll be introducing you to how carbon acids can be used to facilitate the formation of an alkyne, which is an intended outcome, and why it is necessary to pay attention to the strength of the base, such as to avoid any unwanted elimination reactions. These would be an unintended outcome. In video 2 we'll continue two themes. One is another synthetic route towards alkynes. This involves a double elimination of an alkyl halide substrate. And lastly, in videos 3 and 4 we will consider the first set of addition reactions, hydrogenation, which will be applied to alkenes, that's video 3, and then alkynes in the last video, that's video 4. Here on this slide we see some common carbon acids. Now most hydrocarbons don't react as Bronsted acids. Nevertheless, let's imagine such a reaction in which a deprotonation reaction leads to those anions we see on this slide. Now these data, that's the pKa data, firstly tell us that the carbanions are extremely strong bases, that is, that hydrocarbons are very weak acids, and that second, relatively speaking, the alkynes are the most acidic of this series. Alkyl anions and vinylic anions are seldom, if ever, formed by proton removal from the corresponding hydrocarbons. Now that's not to say that vinylic carbanions will not be formed, as we'll see in a later lecture. The base that is capable of removing this is incredibly strong, and the base that is used is called sodium amide. This is one that is dissolved in its conjugate acid, liquid ammonia. The amide anion, NH2- is the conjugate base of ammonia, which as an acid has a pKa of about 35. When we consider the basicity though of the acetylenic anion, this in itself is actually quite high, the pKa value being 25 for the alkyne. Here we see a series of acids and their conjugate bases, and we're comparing the decreasing acid strength and the increase in base strength. So what we can see in the grand scheme of things is that an acetylenic base is pretty basic when compared to others in this series. So what does this mean for any reactions that are carried out using such a base? So we have to be aware of any competing acid-base reactions. For example, if this strong base is brought near phenol, then the only reaction that will occur is the acid-base reaction shown. The weak acid will be favoured, so we do need to consider this and be mindful of the consequences. Now if we flip this, then it comes as no surprise that the phenoxide anion will not be strongly basic enough to deprotonate the alkyne. Hence we will need a much stronger base like the one I mentioned on the previous slide, that's sodium amide, or more commonly known as sodamide. The other consideration is that this strong base can also behave like a strong nucleophile in a reaction, but it is going to be selective. If this strong base, strong nucleophile is reacted with a primary alkyl halide substrate, then in this case an internal alkyne will be formed. Carbon-carbon bond forming reactions are always very useful in organic synthesis. But whilst these species will behave as a good nucleophile, as indicated in the earlier slides of earlier lectures, these acetylenic species will also be strong bases. The danger here is forgetting this and causing an unintended side reaction. Let's have a look at this now. Okay, so I want you to take a moment here to think about what you already know concerning SN2 and E2 reactions. What would you expect to happen in this case? Draw the intended product of the SN2 on the left-hand side and the actual product, the E2, on the right-hand side. Pause the video while you do this and resume when you want to check the answer. Here are both of those products. However, if you were intending a carbon-carbon bond formation via the SN2 reaction, you're going to be pretty disappointed by your yield, as the reaction would most likely give the elimination product. A secondary alkyl halide substrate is more crowded around the carbon center, and so the hydrogens are more likely to be abstracted instead.
This concludes part A.
In this particular video, we'll be looking at something called the double elimination reaction. Now this involves two types of substrate, either a vicinal dihalide or a geminal dihalide. The difference between them is that the vicinal dihalide places the halogen atoms on neighbouring carbons, whereas the geminal, or gem for short, places the halogen atoms on the same carbon. Now in terms of using the vicinal dihalide, what happens is that a beta hydrogen is abstracted by the first of two equivalents of sodamide that are in the reaction pot. Now the hydrogen and the bromine leaving group in this case have to be in an anti-conformation in order for this concerted process to take place. Once the trans-alkene is formed in situ, then that second equivalent of sodamide comes along and is able to abstract the vinylic hydrogen in another concerted process to kick out the bromine leaving group. But again, there has to be the anti-conformation. Now in this case, what happens is we formed an internal alkyne, and that means that this is an alkyne whereby it's not found at the end of the molecule, but it's found somewhere in the middle of the molecule. So let's now take a look at the use of a geminal dihalide and how that can be used to form a terminal alkyne. Here we see that a geminal dihalide is being used to synthesize a terminal alkyne. And these terminal alkynes have the hydrogen at the end of the alkyne chain. It's possible to achieve the same thing with a vicinal dihalide. However, in this case, sodium amide reacts in mineral oil and 3 equivalents are used. I'll explain why in a moment. So the sodium amide abstracts a proton from the methyl group at the end of the molecule. And again, it's necessary that the beta hydrogen, and in this case the chlorine leaving group, are in an anti-conformation for both the geminal dihalide and also the subsequent alkene. Now the third equivalent that I referred to earlier is because as the terminal alkyne is being made in situ, the alkynide proton has quite a low pKa. And so this means that it's readily abstracted by one of the equivalents of sodium amide. And so what's going to happen is that this is going to reduce the amount of the vinylic proton that is capable of being abstracted because it's got a much higher pKa. By adding the third equivalent of sodium amide, what this does is it increases the likelihood of the vinylic proton being deprotonated in the alkene product. And yes, it will also cause the alkynide proton to be deprotonated as well. And the final step then is to use a mild acid which just protonates this all at the end.
This concludes part B.
We're now changing tack and looking at something called the addition reaction, and the addition reactions of alkenes in this particular video. So addition reactions are the reverse of elimination, whereby the pi bond is broken and the molecule is added across the pi bond. One very specific reaction is the hydrogenation of alkenes, which in past lectures I have referred to in passing. This occurs as a syn addition. So the hydrogen molecule will be added to the same face of the double bond, and this is done typically over a metal catalyst. The breaking of a pi bond and the formation of 2 sigma bonds releases energy throughout this process, so these are typically exothermic reactions. Let's now look at the mechanism to understand the syn addition in a little bit more detail. The metal catalyst, in this case palladium, reduces the energy of activation and helps dissociate the hydrogen molecule into 2 hydrogen atoms. These remain attached to the surface of the metal. As the alkene passes over the catalyst, in this case cyclohexene, the pi bond is broken and the hydrogen atoms are delivered to the same face. hence this is why they have a syn relationship. There is the formation of two very strong carbon-hydrogen sigma bonds, and this releases energy as the product is more stable than the reactants. There is a stereochemical outcome here that needs to be considered, and here we have two substrates whereby the first is a symmetrical alkene with Z stereochemistry, and the second instance we have an alkene that has the E stereochemistry. Let's look at these individually. The Z alkene, which coincidentally is a cis alkene, places the hydrogen molecule across the double bond, and when it does so, remember there is an equal chance of the hydrogen being added from the top as there is from it being added from the bottom. Now, irrespective of which direction the hydrogen molecule approaches, the result is a meso compound, which in itself is achiral. Let's have a look at the E alkene now. In the second instance, the hydrogen molecule was also able to approach from either the bottom or the top. Nonetheless, because of the syn addition, just like the last case, this resulted in a chiral product. Now, to be fair, this is racemic, so the other enantiomer would likely be produced in the same amount.
This concludes part C.
In this last video, that's video 4 for chapter 7.3, we're going to cover the addition reactions of alkynes. When an alkyne is treated with two equivalents of hydrogen and a palladium carbon catalyst, then a full reduction is achieved and the alkane product would be produced. However, there is the potential for partial reduction, and dependent on the conditions that are used, these can have different stereochemical consequences. Let's take a look at these now. When we have an internal alkyne, the simplest of which being prop-2-ine, then the partial reduction is achieved by using one equivalent of hydrogen, and with a Lindlars catalyst then syn addition results and hydrogen is added to the same side of the alkyne. This results in either a Z or a cis alkene. If the same alkyne is treated with sodium in liquid ammonia followed by ammonium chloride in a second step, then we see the anti-product. So now it's time to put a few of these concepts that we've looked at over a number of chapters into practice. The purpose of this problem is to get you to go back over your notes. I want to take a look at this retrosynthesis question before asking you to do a very similar pre-lecture problem. Here we're given a target molecule called muscular, and we're asked to synthesize it from ethine or acetylene. In this approach, we start to build up our retrosynthetic toolkit by considering the first truly multi-step synthesis. Firstly, we need to observe the stereochemistry around the double bond and where that might have come from in the first step. So for example, we see that this is a cis or a Z alkene, and this would have come from the partial hydrogenation of an alkyne. So this was the former step, a functional group interconversion. Next, we want to sever the bond, and in this case the book choice is to sever the right hand portion of the molecule from the left. And this would mean having a carbon chain of 8 carbons and the positive charge in a primary position. Seeing as this isn't a benchtop reagent, we can change this to an alkyl bromide. The negative alkanide anion would be able to be stabilized by adding a sodium counterion. However, we're not at the desired starting material, acetylene, but we're close. The sodium or the alkanide salt would not be readily available, and so we would need to convert this to the corresponding alkyne. So we have our next functional group conversion. The alkyne that we now have can be severed again, and this would yield a second acetylide anion and a 12 carbon alkyl halide. Lastly, the acetylide anion would have come from acetylene or ethine. This is what a multi-step retrosynthetic strategy looks like. And now we can take a look at what happens when we come forwards. So the synthetic strategy would be to start with ethine, deprotonate this with sodamide in liquid ammonia, We then, in the second step, alkylate the acetylide anion using SN2 with 1-bromo undecane. Once we have the tridec 1-ine, this is treated with a second equivalent of sodamide in liquid ammonia again to form the alkanide anion. We react this again by a second SN2 reaction with 1-bromoheptane to give the alkyne that we see here. Lastly, the use of hydrogenation with a metal catalyst that is equivalent to Lindlars catalyst adds a molecule of hydrogen via syn addition and yields the target molecule muscular.
This concludes Part D.